Welcome back to the rest of chapter 13. I've added this portion in order to make you aware of the fact how important it is to practice problem solving. It's really important that we understand the symbols we're working with, what these reagents stand for, and how the mechanism dance helps us to put pieces together and understand the outcome of various reactions. So practice, practice, practice. Take notes, draw mechanisms whenever you can and whenever it's needed. And I have to say, if your pencil isn't moving, you are not learning. So you need to move that pencil. It is about the eye-brain-hand coordination to digest the really very complex and often abstract information that's being discussed in organic chemistry. So we're going to start out with one of these examples. So the next few slides will solve various problems. Try to solve it, pause the video, think about what this means. Again, we're using very technical words. We're using a jargon. We need to understand what something looks or stands for and how it affects an overall transformation. So obviously here we have an alcohol, and this is a two-step procedure, and we want to understand what's going on. So the first step is the use of NaH. You should know the name, you should know the Lewis structure. This is sodium hydride. This basically is Na plus H minus. Well, this hydride here will act as a base and actually abstract this oxygen hydrogen, abstract the hydrogen from this OH group. You should know how to draw the curved arrow for this. If I was to just use a placeholder here, because you should draw out this bond when you're drawing curved arrows. So if I was to just draw a portion of this, here's the O, here's the H. Make sure you draw a Lewis structure, which means all non-bonding electrons are shown. I can now utilize my hydride. So H dot dot, strong nucleophile and strong base. In this case, it's going for a net proton. It's making a bond to hydrogen. This can only have one bond, so one electron pair goes over here. So as the intermediate, you get R, O, and there is stereochemistry here, so we can include that if we want it to be that accurate in these notes. So there's this plus a molecule of hydrogen as a side product, which is a gas. And now we're ready for the second step. So this is step 1, NaH. Now what's happening in the second step? So propyl iodide, so this is a halide. So this is an Rx, that's the general group, and the molecule specifically here is a propyl, so 3 carbons, 1, 2, 3, and then we have an iodide. Remember all these SN2 reactions you learned about, delta plus, delta minus. And so now we need to figure out, again, takes 2 to tango, this is the nucleophile, this is the electrophile. So this will be the NuC. One of those lone pairs is being used to attack this as the electrophile. So this is our E with a delta plus in here. And then we can draw the curved arrow. We take one of those lone pairs and make a bond. We're basically now making a bond to add 3 carbons to this oxygen. So that should then lead us to this product here. So the stereochemistry is retained. We have oxygen, and to that end, 1, 2, 3. Always count the carbons. 1, 2, 3. So basically, what we've seen here, you can again recognize that this is an overall introduction of a propyl group onto the oxygen. We have made an ether, so this was from section 13.5, and this is a named reaction, a Williamson ether synthesis. And you can practice this with Skill Builder Review 13.2. The more you practice, the better it is for you, or easier it is for you to figure out the patterns to help you deduce the answers. All right, let's do another problem. What's the correct order of reagents needed for the following transformation? So we're going from an alkene, we're going to an ether, right? So that's why functional group recognition is so important. You should stop the video here because there are 4 sets of conditions, multi-step. 1, 2, 1, 2, 1, 2, 1, 2, 3, 4 steps. Which one will do it? You should actually be able to come up with the set of conditions even without having this possible list in this multiple choice. So what's happening in here? First of all, it's really important to count the carbons. So we see that there's a carbon here and a carbon here and then 2 methyl groups. And there's no oxygen. Can you correlate that? So you should put your finger down. This carbon here is actually this carbon here. This carbon over here with 2 methyl groups, actually this carbon here. Which means the double bond has disappeared and this ethoxy group was introduced into the structure. Now, how can we do that? There may be more than one possible approach when we do synthesis. We want to find the best synthetic method. So here you see various oxymercuration, demercuration reactions. So A and C are oxymercuration and demercuration. So we also see hydroboration. You should basically realize that these procedures here are all hydration reactions that were discussed in Orgo 1. So hydration reactions. But actually, let me make a little correction here. Actually, these 2 here are hydration reactions. This one here is similar. Take a look. What is the same? What is different? We're going from water to actually an alcohol. That's the only difference between the 2. Now, when you discussed hydration reactions in Orgo 1, there was a Markovnikov product or anti-Markovnikov. Turns out that hydroborations give anti-Markovnikov, oxymercuration, demercuration gives Markovnikov conditions. All right. So as I already said, these 2 are hydration reactions. This is not an alcohol, it's an ether. So it has to be one that makes that alkoxy group, that adds that alkoxy group. Let me note that down here, you should actually work your way through and figure out why these are not the conditions. So since this is an ether group, it's actually these particular reaction conditions that makes things work, and that's outlined here. So we use this mercury acetate, ethanol as the solvent. We can think of this as basically using, let me do this like this. So we're using ethanol. So this is basically an addition across this double bond where we make a new bond here and a new bond here. And that is, of course, the Markovnikov addition. And again, the main difference is, even you've seen this before in hydration reactions, so now we've made a small adjustment, put in that alcohol instead of water, and that will then give you the ether. On the next slide, a nomenclature question, so take a look at that. What's the correct IUPAC name for the following structure? Jot it down. Don't just look at the structure and come up with the name. You must write down the structure, analyze it, assign numbers, and in this case, the task is to come up with the IUPAC name. So here we will name this as an oxyrane. And we have the 1 and the 2 position. Turns out that the longest chain is made up by having 2 propyl groups on each side. So those are the 1, 2 dipropyl groups. In the 1 position, we have an ethyl group, so 2 carbons, and the 2 position, we have the methyl group. All right, on the next slide, something else you should pause here and look at this. Now, here the question is, what starting material do you need to use in order to make this epoxide? Pause the video here, write down all the structures, definitely write this down, and then analyze these conditions. But more importantly, wink, wink, stereochemistry. What's the stereochemistry in the starting alkenes? So you need to match the correct conditions. All right, on the next slide, you have the answer. So this basically has to do with, we're using MCPBA. So MCPBA, both of these are valid abbreviations. It's a perbenzoic acid. It's an RCO3H, meaning forming the epoxide here. And the stereochemistry needs to be retained. So it turns out that we have to have this trans stereochemistry in the starting material. And you learn about 2 ways of preparing epoxides: a 1-step procedure with a per acid, or a 2-step procedure forming the halohydrin and an internal closure, eliminating the bromine to form the epoxide. So, but both of them have to have the trans stereochemistry so that you get the product with the appropriate stereochemistry here. See how the longest chain here is up and the longest chain here is down. So that is a trans relationship, so they need to be on opposite sides. Okay, here's another one. So what is the product for the following reaction? Okay, we have an epoxide. It has 2 substituents on one side, nothing on the other side. Can you read the conditions and what they stand for? Well, ding, 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 ding. This is a Grignard. We know that a Grignard reagent like this provides basically a source for CH3 minus. That nucleophile will open up on the least substituted side. When you draw a mechanism, make sure it's a Lewis structure you're working with. Show all the electrons so you don't have problems with figuring out the charges in certain intermediates. So that then leads to oxygen. I'm going to use lines because that's faster. You can use dots. Okay, this carbon is this carbon, and now this is the new carbon. Let me maybe color code it. So I'm just going to put a CH3 here. You can just end the line or write CH3, it doesn't really matter. But that's the component that was introduced here. And we see another representation. You can, of course, have different orientations here. So here it is. It looks a little bit different, but essentially, so this was the methyl group we introduced. And this is the oxygen from the previous epoxide. All right, now here we have another reaction. What is the product for this reaction? Actually, before, look at this one here. These were basic conditions, strong nucleophile. Strong nucleophile with a negative charge. Now here we have acidic conditions. Make sure you work with Lewis structure. So we have lone pairs here. We know that HBr is really H plus and Br minus. We know that we can activate the epoxide through protonation. So make sure the direction is correct. We now have our intermediate activated epoxide. Still have a lone pair here. We made a new bond to hydrogen. We have the rest of the 3-membered ring, the oxyrane. We have stereochemistry. And then this here has a positive charge because we made that extra bond. There's only 1, 2, 3, 4, 5. Oxygen is making the 6. And now we can have Br minus attacking. Where does it attack? Do you know how to work this through? So we're dealing here 2 substituents on one side, 1 substituent on the other side. Here we see Remember that under these acidic conditions, you're actually now favoring the more substituted side. I tried to illustrate that by basically you can draw two resonance forms to this. You can draw this form here. I'm actually breaking this bond. Oxygen doesn't like a positive charge, so it's going to take the electrons. I'm going to draw the rest here. Here's your OH group, and that would be a positive charge here. There is another resonance form possible. Remember, double-headed arrow resonance form. If we open up this line here, that then becomes the lone pair on the oxygen. So then we have another possible outcome. So now in this case, this is being pulled in this direction. Here we have OH. We have our two lone pairs. But we've taken away electron density. I'm going to draw it like this, although this is not going to be very helpful because this can rotate around. But we want to discuss the electronics. Now, which of these two carbocations or intermediates is more stable? Here we have 1, 2, 3 substituents, that's tertiary. Here we only have 1, 2, that's secondary. Tertiary wins. And we can actually equate this with an intermediate that can be drawn like this. So going back to the electronics here, let me make this a little bit more clear. I'm going to draw this a little bit longer. The oxygen is going to be more to the right-hand side, because the more positive character we develop on this carbon, this is going to be the more stable in terms of having the partial positive charge here. Remember, this is protonated. And I'm going to draw this as a dashed line here. Okay, so there is now positive character on the oxygen. But in order to now understand how the reaction finally proceeds, it's this delta positive here that's most pronounced, and therefore the bromine will attack in that position. So one lone pair is going to come here. This will quench the positive charge on here. So that's how we come up with this selectivity here. Okay, so the bromine has been added to the more substituted site here. More substituted site here. More substituted site here. All right, and here we have another one. This is very information dense. Basically, correct order of reagents. You can see it's a 3-step procedure. You should pause the video, copy these two structures, analyze what is the same, what is different, and look at the different reagents you have. So I'm going to give you a minute here. So we can definitely see that this comes together with certain pieces. We have a propyl group here. So that's my C3, C3. C3. All right, the bromine has been replaced with a, let me use this color here, has been replaced with a sulfur. And then we see that there's another component, the propyl group. So it looks like 3 pieces, and we do have 3 steps. So that's what you need to be aware of. All right. Look at your reagents, look at the conditions, how can you achieve it? And I'm giving you a heads up, and if we do this as multiple choice here, so it is a 3-step procedure. Okay, have you done your work? All right, and here is the answer. So we take our propyl bromide, we introduce the sulfur by using NaSH, remember that's Na plus SH minus. That then helps us introducing the SH group. So this is your first intermediate SH. Then we have NaOH. Those are basic conditions. That's Na plus and OH minus. This leads to deprotonation. Let me make this a little bit more clear. I might as well draw out that bond. And when we draw mechanisms, let's make sure we have a Lewis structure, meaning showing all non-bonding electrons, especially where the reaction occurs. So now we have OH minus attacking, making the anion. There we have this. And now all we need to do is figure out what's the electrophile to introduce this. So basically you need an X. So that would be your isobutyl bromide. So that is what gets you there. You could use iodide as well. Thank you for listening.